Okay, folks, so this is going to be chapter 17, which is spontaneity, entropy, and free energy. The other way you can think of this chapter is you may remember last semester in Gen Chem 1, you had a chapter that was based on thermodynamics, right? Or thermochemistry, depending on what book you took it out of. Okay, so this is actually the continuation of that chapter. This is looking at those same concepts, but instead of us just brushing over them, we're actually going to try to understand them. Okay? So remember that this is another kinetics. This is not a kinetics chapter. This is another thermodynamics or spontaneity or energy chapter. Okay? So we're looking again at which direction things will be spontaneous. If you light a fire, will it continue to burn, or do you continuously have to give it energy? This is in direct contrast to the kinetics chapter that we did before we did all those ice chapters. I know many of you probably don't remember that chapter so well at this point because we've had a lot of stuff since then. But anyways, keep in mind that kinetics is different than the spontaneity or the energy. Okay? Kinetics is how fast something will be going. Spontaneity says if it's spontaneous, it'll go forward under its own energy. If it's not spontaneous, then you would continuously have to provide energy or it will go the other direction. Alright, so this chapter has quite a few sections to it. And we're going to start off with actually what is mostly review, or at least should be. Thermodynamics. So the first law of thermodynamics states that the energy of the universe is constant. So this is a statement of the law of conservation of energy. This is that energy can be neither created nor destroyed, that hopefully in the back of your head is playing continuously. Now, an interesting little side note to this is before the first law of thermodynamics was stated, and then they tested it many, many times, and it was said, they went, yeah, this is a law. We see this all around us all the time. People literally used to think that the world worked like, best analogy I can give you these days is like a video game, where literally items and monsters, literally monsters, would pop out of nowhere. They used to literally think if you sailed along the sea, a large sea dragon would just pop out into existence. Bam, you have a large sea dragon, now it eats your ship. That used to be the common thought process. Nowadays, even if you're superstitious, you think it comes from somewhere, right? Because we all have this ingrained in us now that things are not created nor destroyed. They come from something. They're just recycled, right? So people would literally open closets and, there wouldn't be any money in there. They'd open a closet again, they'd think money would just pop in there. That things literally just popped into existence with no preceding meaning behind it. So it's an incredibly difficult thing to envision this thought process because almost everybody in the modern age simply has been raised on the first law of thermodynamics. So, spontaneous process, this is going to occur without external intervention. The best example I can give you all the time is a boulder rolling down a hill, or a bonfire is going to continuously burn until it runs out of fuel, right? Now, this spontaneous process, this can be fast, this could be slow. For example, the Grand Canyon was formed through spontaneous processes. But it took millions and millions of years for it to form, so it was very slow. Rusting happens spontaneously. That happens over decades, right? Or years, depending on what you're talking about. So that is also fairly slow. Whereas an explosion happens spontaneously, but that is very fast, right? All right, so again, the domain of kinetics, this is going to be the rate of a reaction. And this is going to depend on the pathway from the reactants to the products. You can think of it being like the pathway down a mountain. You could have a long winding pathway, in which case your kinetics can be very slow, or you could have a very short drop off, in which case your kinetics would be very fast, right? Thermodynamics, on the other hand, is going to provide you the information on whether a reaction will be spontaneous, based only on the properties of your reactants and products. And so thermodynamics is like starting on the top of the mountain versus starting on the bottom. If you start on the top, then you could roll down the pathway theoretically and not need to use any of your own energy. If you start on the bottom, you would have to use your energy to scale the mountain, right? To go upwards. And so that would be your thermodynamics section that we're in right now. Okay, so there's two different types of energies we have to talk about when we talk about thermodynamics. The one that you guys probably know of already is enthalpy, which is heat energy under constant pressure, and that's the one you should have learned for last semester and explored up to a fairly decent degree. The one you probably don't understand yet, and you may have heard of, but you almost certainly don't really understand it, is entropy. So this is going to be a thermodynamic function that describes the number of arrangements that are available to a system existing in a given state. Now, most people are going to say, and this is actually a decent analogy, but it can cause a little bit of confusion because these words are widely spread and used. And that is the measure of a molecular randomness or disorder. So many people say this is a measurement of randomness, disorder, chaos. The problem is all of these words are loaded words and bring along connotations that just aren't there. So entropy, the best definition I can give you is this one right here. It's literally counting up the number of different arrangements your molecules could be in. The more arrangements they could be in, the more entropy. Okay? That's probably your best definition. That's your best way of truly understanding entropy. I'll give you a bit more material and background to understand it a bit better, but that actually does a good job if you just think that through. Entropy is actually denoted by the symbol S. And so if you have delta S, that's change in entropy. And it is always the capital S, remember that, because the lowercase s commonly is used for speed, right? And so you do have to be careful about that. Okay, so here's an example of entropy acting and causing something to be spontaneous. So the natural spontaneously proceeds towards the state that has the highest probabilities of existing. So here we see two different states. We start with a glass cylinder here. Excuse me. A glass flask here, round bottom flask, or container, whatever, that is currently separated from one that is under vacuum. And so we have a gas on this side, we have a vacuum on this side. Now, if you open this stopcock, that's what those are called, by the way, they have a little hole right here, you would let the gas through, and what you would expect to see is that the amount of gas in both sides, if these are same volume, pressure, everything else, would be equal. And so that is because this is the state that has the highest probability of existing. This is actually being driven by entropy. Now, one of the things that I get a lot of people sort of blanking out on me when I talk about entropy, because most of you think that everything's driven by enthalpy or heat, right? And that's not an uncommon thing. There's nothing wrong that you started that way. However, many of your pathways in your body, for example, many of the ions move through your cell wall, your cell membranes, excuse me, I don't know why I keep giving wrong words, your cell membrane through shedding molecules of water. And this is actually an entropy-driven, spontaneous process. And so many of the ions that go through your cell membrane and go into your cells and then cause all your proteins and everything else to function. Those are actually driven through entropy processes. Gases typically are mixing due to entropy processes. When you put in soda with water, eventually they'll form an equilibrium where the whole thing is just the mixture, right? It doesn't have separate parts. If you put dye in water, it'll slowly spread. These are all entropy-driven processes. So you've actually been surrounded by many different entropy-driven processes. You just didn't know it. All right, now, when we talk about entropy, we need to talk in microstates so that we can understand the macro state. Now, macro state is the bulk arrangement of everything, right? However, microstates are going to be, you guys all hopefully know that micro means small, right? Macro means large. So microstates, small states. Macro state would be the overall state. So here we see each configuration that would give a particular arrangement. And that is what a microstate is. It's the arrangement of the individual molecules that would give you a single state. And so you can have many possible arrangements for even just 4 different molecules. You see this? These are the arrangements you could have just for 4 molecules. The probability of occurrence of a state is going to depend on the number of microstates in which the arrangement can be achieved. And so the state that is the most likely to happen is going to be the state that has the most microstates to it. And this is going to be the one that is the spontaneous typically, or is driven by entropy. Okay, so right here we see arrangement 1. We have all 4 molecules on the left side. We move 1 to the right side. That's arrangement 2. We move 2 to the right side. That's arrangement 3. 3 of them move to the right side. You get the pattern, hopefully. All right, so we can count up these number of microstates from those arrangements. And so right here, we see this is a number of microstates for this arrangement. So this arrangement where all 4 are on the same side. This only has a single microstate. Because they're all on the same side, we can't identify, A, B, C, D, they're all on the same side. That doesn't matter that they're different molecules. There's no difference. Arrangement 2, you can move A to the right side, you can move B to the right side, you could move C instead to the right side, or D to the right side. So there is actually 4 different microstates from this arrangement of 3 on the left, 1 on the right. Because depending on which molecule moves over, you would have a different microstate. Now, the arrangement where we have 2 on each side is going to have 6 microstates because again, we can match different molecules on each side to give us a total of 6 different arrangements. All right, and right here we see 5. Again, this is going to have 4 microstates. Really, 4 and 5 are just flips of this. We just flip these around. And so 5 has 1 microstate. And so the one that has the greatest number of microstates is the most likely to happen, and that's that they equally divide on both sides for your macrostate. So positional probability, this is going to depend on the number of configurations in space that yield a particular state. So gas expands into a vacuum to give a uniform distribution. The expanded state has the highest positional probability of the states available to the system, which is what we just proved right here. All right, so let's look at positional probability and changes of state. So positional entropy is going to increase when going from a solid to a gaseous state. And the reason for this is a solid, all the particles are very tightly contained. And so they don't have a lot of different positions they could be in. They don't have a lot of options. When we go to a liquid, this is going to have a higher entropy because this has more states, microstates, that it could fulfill. Because you can move these individual particles into more different positions and arrangements. Now, when we go to a gas, this is going to have a massively increased number of microstates. Typically, you have more volume, but the biggest issue is these have all different arrangements in the directions they're moving, where they are in space, so they can contain the entire room rather than just inside a beaker and not even the whole beaker. Uh, these can also be different distances from these. These all have to be relatively near to each other. These can be any distance from each other. So you have a vastly larger number of positions a gas can fulfill. That means it has a much, much larger entropy. So entropy change when mixing two pure substances is also expected to be positive. The result of the presence of more microstates for the mixed condition. Think about it this way. If you had everything on the left and right, they're more organized, right? When you mix them together, you have more different positions. You could have AB next to each other, you could have AA next to each other, you could have BB next to each other. You have many different arrangements suddenly that become available. Caused owing to the increased volume available to a given particle after mixing occurs. Again, you've also increased the volume that you can fulfill by mixing two different substances together. Before, each of them may have been half a liter, and so each had half a liter that they could be in, that they could have different positions in. When we mix them together, they now have a full liter that they can occupy. The formation of solutions is favored by an increasing positional entropy that is associated with mixing. So let's go ahead and try a little bit of an interactive example. So for each of the following pairs, choose the substance with the higher positional entropy per mole at a given temperature. One of the things I would like to point out before we go into this interactive problem is we can do those pure number of positional entropies when we're talking about like 4 molecules. It wasn't too hard to do. Keep in mind that when you try to do things that are a mole is 6.02 times 10 to the 23rd. It's a lot of particles to keep track of. So we're not going to be doing that for anything larger than just a few particles, okay? That's just a visual example that you can use to understand entropy better. Please don't get stuck on it. All right, now let's try this solid CO2 going to gaseous CO2 and compare those. Then we'll try the N2 gas at 1 atmosphere and the N2 gas at 1.0 times 10 to the negative second atmosphere. All right, so a mole of gaseous CO2 will have a much greater volume, and the molecules have many more available positions than the solid would, because they can be very far apart or they can be very close, whereas the solid all have to be bound together. And so the gaseous CO2 has the higher positional entropy by a very large amount. A mole of N2 gas at 1 times 10 to the negative 2 atmosphere has a volume that's 100 times that at a given temperature of a mole of N2 gas at 1 atmosphere. That again is that PV equals nRT. That would be that relationship. So that gas at a lower pressure should have a higher positional entropy. It has more positions that it can fulfill. So let's predict the sign of the entropy change for each of the following processes. We have solid sugar is added to water to form a solution. Iodine vapor condenses on a cold surface to form crystals. So when you add the sugar molecules to the water, they're going to become randomly dispersed in that water, right? So you are forming a solution. That's going to give it larger access to volume. It's also going to increase the number of possible positions of it, and it will also increase the number of different arrangements it can have. And so you would expect the positional disorder to increase, and that means an increase in entropy, because remember, the entropy is related to positional disorder. It's one of the ways we can find that. We can also think of this as the delta S, which would be change in entropy. Hopefully you remember that change in delta always means final minus initial. And so this should give us a positive delta S, since the final state will have a larger entropy than the initial. Gaseous iodine forming a solid. So this process here involves a change from a relatively large volume to a much smaller volume. You were a gas that took up a lot of volume, that you could fill the entire room if you wanted to, or whatever flask it was contained in, whatever sealed container it was contained in. This can result in lower positional disorder if you then collect that all onto a surface as a solid. So for this process, your delta S will be negative. So your entropy will decrease. Which of the following substances has the higher positional probability per mole? Well, of course, that's going to be gas. The gaseous water at 100 degrees Celsius. Because gases always have much larger positional probability or positional entropy per whatever unit. Predict the sign of the change in positional probability for the process of dry ice, which is solid CO2, sublimating to form gaseous CO2. Well, of course, that's going to increase your positional probability or your entropy, right? Because you're going from a solid to a gas. So the second law of thermodynamics, in any spontaneous process, there is always an increase in the entropy of the universe. The universe's entropy always goes up. Now, you may have actually heard this before. It's a very popular thing that's out there. That's sort of a subtext of many different science fiction, superhero stuff, just pop culture in general. So the first law of thermodynamics, the energy of the universe is constant, and the energy is conserved, but the entropy is not. So entropy is actually going to continuously increase in the universe overall. So the delta S of the universe always has to be positive. Now, the delta S of the universe, this is going to be composed of, like everything else in science, the delta S of our system, whatever we define, plus the delta S of our surroundings. And remember, system is whatever we define as the system. Surroundings then is everything else in the universe. And so anytime you talk about the universe, you can always split it between system and surroundings. It's a wonderful, nice way that you can deal with the universe and not have to blow up your head because it's, approaching infinity. So the delta S of the universe is positive. The entropy of the universe increases. The process is spontaneous in the direction written. The delta S of the universe is negative. That process is spontaneous in the opposite direction then. So if you come up with some process, so for example, a solid going to a gas, that delta S of the universe is positive, then that will spontaneously occur. Okay, so that solid will sublimate spontaneously. It'll do it on its own. If the delta S of the universe is negative, however, it would actually go in the opposite direction. And so it would spontaneously go from the gaseous state to the solid state. All right? Now you may notice at this point that we've been talking about these and talking about spontaneity. Yes, this is related to the previous work you did on spontaneity and the previous equilibriums you did. Those values of KSP, all that, those are related to this. And I'll give you a little bit of information, but that's a bit more of an advanced thing to go really far into it. Okay? Now, the delta S of the universe is 0. This process has no tendency to occur at all. The system is actually at equilibrium. In a living cell, large molecules are assembled from simpler ones. Is this process consistent with the second law of thermodynamics, that the overall entropy of the universe always has to go up? By the way, in case you are having trouble with remembering the delta S of the universe, it always has to be positive, that's spontaneous. One of the ways that people can remember this easier, and I find really helps, is you always have to pay the piper. Okay? And if you think about that statement, the universe is the piper, right? You have to pay it in entropy. All right, so in your living cell, we're looking at is this process spontaneous according to what we've just learned? So to reconcile that operation of the order-producing cell with the second law of thermodynamics, because your cells are making things more ordered. Otherwise, that would be chaos and nothing would happen. So how can we reconcile that with the delta S of the universe always increasing? Well, is our cell the entire universe? No. No, our cell is actually delta S system, isn't it? So that means that as long as there's a positive process somewhere else in the surroundings, the delta S of the universe will be positive overall. So again, remember, the delta S system does not have to be positive. It can be negative. The delta S of the universe has to always be positive for it to be spontaneous. A process for which the delta S system is negative can actually be spontaneous if your associated delta S surroundings is both larger and positive, so that you will get an overall positive delta S universe. Operations of a cell are typically this sort of process. They're actually being driven by spontaneous processes happening in the system around them. So for which process is delta S positive? Water freezing at negative 20 degrees Celsius, ideal gas being compressed reversibly at a constant temperature and pressure, precipitation reaction. Let me get water. Spontaneous endothermic process at a constant temperature and pressure. Well, if it's a spontaneous endothermic process at constant temperature and pressure, then this actually has to mean that the delta S would be positive. Keep in mind, for this endothermic process, your delta S of your surroundings would actually have to be negative. And so what we're looking at here is, for it to be spontaneous, that means the delta S of the universe has to be positive. Endothermic means the surroundings is negative, and so your delta S of your system here has to be positive, because we know the other two terms. So for any spontaneous process, which of these? Delta S universe, okay, hopefully by now you've realized that it's the delta S of the universe only that has to be positive. It's never any of the other ones. It's only the delta S of the universe that is counted, that is positive for this second law of thermodynamics. So your entropy changes in your surroundings. Delta S of surroundings is determined by the flow of energy as heat. This is actually referring to those exothermic and endothermic processes that we've talked about before. So the exothermic process will increase the delta S of surroundings. That's an important driving force for spontaneity. This is why many of the things that we associate with being spontaneous are also exothermic, and that's why we have that tie-in. Endothermic process decreases delta S of surroundings, which means that your delta S of your system would then have to be positive to make the overall reaction spontaneous. The impact of transfer of energy as heat to or from the surroundings is greater at lower temperatures. This is why later on you will see that this will have a temperature dependency. And this is why you actually know this fact that, for example, when you put water in a cool environment, in a low temperature environment, it can form ice, right? And that's the spontaneous process. But when you put water at a higher temperature environment, like room temperature, it will spontaneously form into the liquid form. Again, that's your temperature dependence right there. So signs of delta S surroundings is going to depend on the direction of your heat flow. So at constant temperature, assuming your temperature isn't changing while this is happening, the delta S surroundings for the exothermic process is going to be positive. Your delta S surroundings for the endothermic process is going to be negative. Your magnitude of your delta S surroundings will depend on your temperature, typically registered in Kelvin, because that's an absolute temperature scale. All right, so remember, the exothermic process, you have a positive quantity of heat, that would be in joules, that's in energy, divided by the temperature in Kelvin. The surroundings to be negative, then for an endothermic process, is going to give you negative quantity of heat over your temperature. By the way, quantity of heat is usually called Q. And so you may have noticed that we are actually looking at a very special term that you have encountered before. So you can call your delta S of surroundings in terms of delta H. So a process that occurs at constant pressure then, which you remember that delta H is the heat flow or heat at constant pressure. So your heat flow equals your change in enthalpy at constant pressure, which is the same thing as your delta H. So the components of your delta H are your sign, which again indicates your direction of flow, doesn't it? This is going to be determined in accordance with your reaction system. Your number, that's going to indicate your quantity of that energy. So right here we see the reaction takes place under constant temperature and pressure. Then we can call the delta S surroundings equal to the negative delta H over T. And you see now that these are actually directly related. They are inversely proportional. So if the reaction is exothermic, your delta H will have a negative sign, your delta S surrounding will have a positive sign, because your heat will flow into the surroundings. Okay, and there you go. That's how the delta S and delta S surroundings and delta H are related. I know. All right, so right here you see a different summary of what we just talked about. Honestly, the table is somewhat useless, but if you're having trouble relating how these would relate to each other, there you go. In the metallurgy of antimony, the pure metal is recovered via different reactions depending on the composition of the ore. So iron is used to reduce antimony and sulfide ores. And right here we see the antimony sulfide with iron, reacting with iron, solid, gives us the antimony solid and the iron sulfide. And this has a delta H of negative 125 kilojoules. And that tells you that this is an exothermic reaction, doesn't it? So carbon is then used as the reducing agent for the oxide ores. And so right here we have the antimony oxide, and we add carbon, typically in the form of like charcoal, or usually in the form of charcoal, or coal of one form or another. And this would give us our antimony solid and carbon monoxide. This has a delta H of 778 kilojoules. Notice that is an endothermic reaction. So calculate the delta S surroundings for each of these reactions at 25 degrees Celsius and 1 atmosphere. The 1 atmosphere is actually there so we know that this is constant pressure. The 25 degrees Celsius, we both need that temperature, and it tells us this is constant temperature as well. So we can do this equation. Okay, so this equation right here is true if we have constant temperature and pressure. And that is the delta surroundings equals the negative delta H over T. So T will equal 25 plus 273, which gives us 298 Kelvin. We've just done the conversion to Kelvin from degrees Celsius, so that we could plug these values into this delta surroundings formula. So we plug in our delta H up here. Notice we are negative, negative, so that's going to become positive. Then we divide by the 298 Kelvin, the temperature. And that will give us this value right here in kilojoules per Kelvin. We really want this in joules. Whenever we talk about entropies, we typically are going to list them off in joules per Kelvin. And so the delta S surroundings is 419 joules per Kelvin. So this delta S surroundings is going to be positive since the reaction is exothermic. Something you should always go ahead and double check. It's exothermic. This is positive. Excellent. And so our heat will flow outwards towards the surroundings. This will increase the randomness of your surroundings. So right here is the oxide ore reaction. So again, we've plugged in that I have a negative that should not be there. I'm sorry about that. There is no negative here. Let me go ahead and fix that. Sorry about that. I can't fix that. That's a graphic that I got from your guys' book. Okay. So this negative is not there. It is overall negative. This is 778 kilojoules, again over the temperature. This will be a negative 2.61 kilojoules per Kelvin. We go ahead and convert this to joules. Again, how do you go from kilojoules to joules? Well, you multiply by 1,000, right? And so this is times 1,000, or 10 to the third. Okay, this right here, the delta S surroundings is negative because our heat will flow from the surroundings to our system. All right, now, you may have noticed that this is somewhat clunky and difficult to do if you want to figure out spontaneity, because you have to do a number of different transformations, right? And so literally this is the only reason this entire portion of this chapter exists. If you want to figure out spontaneity, it's much easier to figure out what is called free energy, which is G. So G is what is called Gibbs free energy. And Gibbs was a person, and this person figured out spontaneity and made really some nice, very easy to use calculations that you could figure out if a reaction was going to be spontaneous or a process was spontaneous. So Gibbs free energy is equal to the enthalpy minus the temperature times entropy. And this would be for a given Gibbs free energy. Now this isn't very useful because you may not be aware of this, but figuring out the absolute energy of almost anything is very nearly impossible. We've only figured out the absolute energies of 3 systems in the entire history of chemistry as of this date. And the last time they had to do it, it took them about $1 million, and they made a quantum computer that actually destroyed itself when it did the calculation. So this is actually very hard to figure out this value. However, at constant temperature, you can actually figure out the change in Gibbs free energy. So delta G. And that will equal delta H minus T times delta S. And these values are actually much easier to figure out because you can figure out the before and after, right? You can figure out reactants versus products. Figuring out an absolute value is actually very difficult. So all quantities refer to our system in this. We've defined everything based on our system. This was the previous problem with what we were talking about, is how in the world do you measure surroundings or universe? Are you going to go and every time you want to figure out how much energy it takes to light a match, you're going to go around and, measure how much energy was in star XYZ and how much energy was on this other planet. And, it took you a billion years to figure this problem out. This doesn't make any sense. You simply can't measure surroundings sufficiently. So you need everything defined from system. And this is the brilliant thing about Gibbs free energy, is this has defined everything from system. So this is delta G of your system, this is delta H of your system, and this is delta S of your system. This would also, of course, be temperature of your system. So you can get everything from your system, which you have there in front of you in your lab. So divide both sides of the equation. We can get this in this form right here. So if we divide both sides by T, this will give us the negative delta G over T equals delta H over T plus delta S. Now, at constant temperature and pressure, your delta S or your surroundings equals the negative delta H over T. And so we can see and we can prove to ourselves that this is actually just a repeat of what we already knew. That's where the Gibbs free energy actually came from, is that our delta G over T, negative delta G over T, actually equals the delta S of the universe. Because this right here is delta S surroundings, this right here is delta S systems, and so these all equal each other. So remember that the delta G over T, negative delta G over T, actually is the delta S of the universe. So, and that's at constant temperature and pressure. So a delta G means a positive delta S of the universe. Okay, so hopefully at this point, let's try to go A equals B equals C and connect things. So remember, a delta S in the universe being positive meant it was spontaneous. So if you get a negative delta G, that means your reaction or your process is spontaneous in that forward direction. Now, if you get a positive delta G, then that means the process was spontaneous in the reverse direction. So for example, the forward direction, it would be a negative delta G to say a boulder rolls downhill. It would then be a positive delta G to say the boulder goes up the hill. It needs energy continuously provided to it. If you are in equilibrium, that would be a delta G equals 0, wouldn't it? Because delta S, a universe, being 0, meant you were in equilibrium. There was no overall drive to go either direction. Okay, this again is just a chart showing you the different combinations and what they would indicate, just like we saw before. Alright, so let's go ahead and try a problem here where we can do some calculations, use a little bit of math. You will notice the math actually is fairly straightforward and simple now. The thing you have to be careful about is really only units, okay? Keep track of your units. This is something I hope that you all have sort of playing in the back of your head. Write your units down, keep track of your units. So at what temperatures is the following process spontaneous? At 1 atmosphere. And here we have a delta H naught, that would mean a standard delta H at 31 kilojoules per mole, a delta S naught of 93.0 joules per Kelvin mole. So what is the normal boiling point of liquid Br2? This is boiling, by the way. It's going from a liquid to a gas. Okay, so the vaporization process will be spontaneous at all temperatures where your delta G is negative. So what you really want to find is where delta G is 0, because that's the cutoff point right before it becomes negative, right? So delta S naught favors that vaporization process, which you probably would have imagined, due to that positional entropy increase that we had talked about before. The delta H naught favors the opposite process, which is exothermic. So these opposite tendencies will give you a balance at the boiling point of liquid Br2. Since at that temperature your liquid and gaseous Br2 will be in equilibrium. And so at delta G naught equals 0, that will be your equilibrium point, where you have both the liquid and gas coexisting. Any value below that would be negative, and it will spontaneously go towards the gas. Any value above that will be positive, and it will spontaneously go towards the liquid. So we can find this temperature by simply setting delta G naught equal to 0. By the way, this is one of the common things people get stuck on. When you're trying to do problems and you're trying to figure out the cutoff point where something would become spontaneous, you always want to set delta G equals 0, because that's always your cutoff point before something becomes spontaneous. Right at 0 is right before it becomes spontaneous. So, again, delta G equals delta H minus T times delta S. And so we set delta G equals 0. We have delta H and delta S, so we're going to go ahead and put 1 on each side here. So we go ahead and solve for T here, and delta H gets substituted in. Notice we've converted this from kilojoules to joules, which is just times 1,000, right? We've went ahead and substituted in our delta S, which we don't really have to do anything else to because it's joules mole. That will give us Kelvin. And so this gives us a temperature of 333 Kelvin. Right at that temperature, you would have both forms. You'd have the gas and the liquid in equilibrium. If you go anywhere below that temperature, you're going to start seeing the liquid forming spontaneously. Anywhere above that temperature, you're going to start seeing the gas form spontaneously. By the way, one thing that people sometimes have difficulty understanding here is that, okay, so 0 means exactly 0, right? So you could have a negative 0.00000000000, you know, as many zeros you want, 1 delta G, and that would still be spontaneous. Yeah, it wouldn't be super spontaneous, so yeah, sure. They wouldn't have a huge amount of energy driving it, yeah. But even at 0.000 whatever, how many ever zeros, 1 delta G would still be spontaneous, okay? So, I already told you that. Yeah, I got ahead of that, didn't I? Anyways, you got that. So, by the way, this is the normal boiling point, 333 Kelvin, because this is the point where you start transitioning from liquid to gas or gas to liquid. It's your equilibrium point between the two. All right, this is just a problem that you can check your understanding if you want an extra problem. So a mixture of hydrogen and chlorine remains unreacted until it is exposed to ultraviolet light from burning magnesium strip. When the following reaction occurs very rapidly. So we have here hydrogen reacting with chlorine, or chlorine, and forming HCl. Excuse me. And this has a delta G of negative 45, delta H, and a delta S. So select the statement that best explains this behavior. So the reactants are thermodynamically more stable than the products. The reactants have a small equilibrium constant. Ultraviolet light raises the temperature of the system and makes the reaction more favorable. Negative values for delta S slows down the reaction. Reaction is spontaneous, but the reactants are kinetically stable. Okay, so again, all of our delta H, delta G, and delta S are negative. And so again, these have nothing to do with the speed of the reaction, do they? They just tell you the direction of spontaneity and whether it's exo or endothermic. And so this tells you that this is a spontaneous reaction, yes. This tells you that this is giving off energy. However, we don't have anything right here telling us how fast this reaction is, how easy it is to overcome that activation energy. And so what this statement here does is this is telling you that ultraviolet light here is needed to make this reaction go so you can see it happening. And so what this is really telling us is that ultraviolet light, that's probably what needs to, the energy that takes to overcome that activation energy, and that's kinetics. That's not thermodynamics. Which means the reaction is spontaneous, which, yes, it is, delta G is negative, but the reactants are kinetically stable. They don't move, they're not reacting very quickly. They're just reacting slowly before you add that UV light. So for the vaporization of a liquid at a given pressure, delta G is positive at all temperatures. Delta G is negative at all temperatures. This does not have A, B, C, D. Okay, delta G is positive at low temperatures, but negative at high temperatures. Delta G is negative at low temperatures, but positive at higher temperatures. All right, so there's two kind of ways to think about this. I'm going to flip up the answer real quick, which is right there. And let's go ahead and talk about how you get there. Now, there's two ways that I would think about this problem. So you have a vaporization of a liquid at a given pressure. The given pressure is nice information, sure, but it's not the key factor here. The key factor is this is a vaporization of a liquid. And so you can do two things to think about this. You can use logic, or you can use the formulas that I've already given you. So logically, things vaporize when you get hotter, right? And things would go to liquid when you get cooler. And so you know that delta G is positive when things are spontaneous in the reverse direction. So we have vaporization of a liquid. So delta G will be positive at low temperatures, meaning it would go towards the liquid spontaneously. It would go away from the vapor spontaneously. But negative at higher temperatures. So higher temperatures, you would expect this to vaporize. That means delta G would be negative, right? Meaning it would be spontaneously going to the vapor from the liquid. Okay, so that's how you could deal with this logically. Mathematically, you can actually just list out the formula that I've given you. Delta G equals delta H minus T delta S, just like we had seen before. And what you could do is play with the numbers a little bit. So whenever we're talking about the vaporization of a liquid, that takes up energy, doesn't it? So delta S is a positive value. Now, I'm sorry, did I just say delta S? Oh my goodness. Delta H, enthalpy, is a positive value for the vaporization of a liquid. Delta S, on the other hand, is going to also be a positive for the vaporization of a liquid. You will increase your entropy. Now, for something to be spontaneous, that means that at low temperatures, your delta S is going to have less effect on your delta H. At higher temperatures, that's going to have a greater effect. That means that your delta H isn't changing. So we can sort of ignore that. We can just go, that's a constant. It's not changing here. Your T is the thing that's changing here. So that is minus T delta S, right? So at low temperatures, T is small, and your delta H would be positive because that delta G would be positive because that delta H is positive. At higher temperatures, that T would be larger, the minus T delta S would be a larger negative value. And that's going to overwhelm your delta H number, which will give you a negative delta G. I honestly usually find in these problems it's better just to think about things you actually know about in your life. Like, I know that, water vaporizes from a liquid at higher temperatures. And then use the vocabulary and concepts I've taught you to, give me the answer. In which case, must a reaction be spontaneous at all temperatures? So of course that's going to be when delta H is negative and the delta S is positive, because then your temperature won't matter. They're both going in the same direction, which is spontaneity. At constant pressure, the reaction 2NO2 yields N2O4 is exothermic. Reaction as written is what? Well, this is going to be spontaneous at low temperatures, but not at high temperatures. This is, okay, so the funny thing about this is you've actually seen this same reaction in a number of the different chapters. That equilibrium chapter, I showed you this reaction multiple times. I always showed you that this was spontaneously going towards this when you had ice, and then when you warmed it, it was spontaneously going in this direction. So you actually may have remembered this and been able to just answer this from memory. But you have everything you need in this statement to answer this. And that's that constant pressure, this is exothermic. Exothermic means that the delta H is negative. This right here shows you have two particles on this side. You have one particle on this side. So this would actually have greater entropy, wouldn't it? Because you have more possible positions. And so at higher temperatures, you're going to have this side spontaneous because the delta S, again, is multiplied by T. So the higher the temperature, the larger that value. This will be spontaneous at lower temperatures, going in the exothermic direction. When a stable diatomic molecule spontaneously forms from its atoms at constant pressure and temperature, what is true about delta H? That is delta H is negative. So you have a stable diatomic molecule spontaneously forms from the atoms at constant pressure and temperature. So your delta H, okay, so before you have two atoms, right? When you form those into a diatomic molecule, you'll only have one atom. This means that delta S is actually negative. That is less positional entropy due to the fact that you can take up less positions. Now, that means that if we have any hope of this being spontaneous at any temperatures, the delta H actually has to be negative. When a stable diatomic molecule spontaneously forms from its atoms at constant pressure and temperature, what is true about delta S? Well, delta S is negative. Because, again, you have less positions that you can fill when you have less molecules or particles to fill them up with. When a stable diatomic molecule spontaneously forms from its atoms, really everything else was meaningless, just this is spontaneous, and so if it is spontaneous, delta G is negative, period. That's all you need to know. Really anything else in this is extraneous junk information. A liquid is vaporized at its boiling point at constant pressure. What is true about delta H? Alright, so this is one of those many cases where if you read this problem and you spend too much time looking at the problem itself and not thinking about what you already know, you can get tripped up. But you have something boiling, right? So liquid is vaporized. What do you have to do? You have to provide energy to a liquid to bring it into the vapor phase, right? That means that the delta H has to be positive. It has to be endothermic, right? Because that's what all vaporizations are. Really, this is not even a question for this chapter per se, just using language from this chapter. This really is a question that you probably knew for halfway through General Chemistry 1. A liquid is vaporized at its boiling point at constant pressure. What is true about delta S? Well, a liquid going to vapor, delta S has to be positive because you have greater number of positions you can take up. A liquid is vaporized at its boiling point at constant pressure. What is true about delta G? This has an equilibrium, right? At the boiling point is when you have both phases existing. So at the boiling point, you still have liquid, and in this case, it may be going to vapor, but you still have some of the liquid. And so the liquid going to vapor, this is happening at delta G0, the equilibrium point. And so the equilibrium points for these are always the boiling temperatures, or the boiling point. So entropy changes in aqueous solutions. We can predict the sign of the delta H solution. It is actually quite difficult. This is because the delta H naught of solution is going to contain positive and negative contributions that are actually quite large. And so there's a lot of information you'd actually need to have to fully predict the delta H naught of a solution. So even if the delta H naught is positive in that solution, it is not expected to be so large it would overwhelm the expected positional value of delta S naught of that solution for this process. This is, of course, forming a solution. The overall effect is to make the delta G negative, and the solution would therefore form spontaneously. Again, most times the delta H's, yeah, both components are quite large. You have large positive, large negative, but typically their differences aren't that large. And so typically these are completely overwhelmed by your delta S, which is the fact that you're mixing, increasing volumes, and increasing the number of microstates that you can make out of having more different types of particles. And that will overall typically give you a larger negative delta G, which makes making solutions typically a spontaneous process. And this is why normally when you add something that would dissolve in water, it will slowly mix throughout the solution. It'll slowly form a solution and mix throughout. Alright, now, following values of delta S naught for KCl, LiF, and CaS forming aqueous solutions. This will illustrate this point. The nature of water as a solvent. Okay, so here we have our KCl. Our delta S solution, in this case, is positive. Right here we have lithium fluoride. Our delta S solution is negative here, negative 36. And calcium sulfide, our delta S of solution right here is negative 138. So what we're seeing here, this difference in these delta S's, is the polar water molecules are attracted to the ions to form hydrated species. So assembling of a group of water molecules around the ions is an order-producing phenomenon. And this would be expected to make a negative contribution to delta S solution. And that's what we're seeing right here, actually. Hydration effect will be greater when the ion possesses more charge density. So the smaller the ion is, with the larger the charge, the greater this effect becomes. Which is what we're seeing here again. This right here is a 2+ charge. Lithium is the smallest metal you can get, and fluoride is the smallest nonmetal you can get. And right here we see calcium, chloride. These are both large, and they don't have a particularly large charge. So they have poor charge density. these have very large charge densities in comparison. And so their hydration effect is much greater, giving you a larger negative delta S solution. Whereas this actually has a positive delta S solution. So for the dissociation reaction of the acid HF, delta S is negative. Which statement best explains why delta S is negative? So the first statement, each HF molecule produces 2 ions when dissociates. B, ions are hydrated. C, reaction is expected to be exothermic, so delta S should be negative. D, reaction is expected to be endothermic, so delta S should be negative. Of course, this is going to be ions are hydrated. So this case, delta S is negative. Well, each HF molecule producing 2 ions, when dissociates, that should have given you a positive value for delta S. This one, the ions are hydrated, would give you a negative delta S value because you're pulling in waters that are now fixed in position, or more fixed in position, if you will, around those H pluses and F minuses. And these, of course, don't actually say, we didn't say anything about what's spontaneous here at all. So these don't actually make any sense. Entropy changes and chemical reactions. So positional probability determines the changes that occur in a chemical system. The fewer the molecules, fewer possible configurations. So if we have more molecules, we have more possible configurations. Less molecules means less configurations. Well, what does that mean? Over on here's side, we have 1 plus 3, which is 4 different molecules here. Over on this side, we're going to cut that down in half. So there's only 2 molecules. And so what we see that we actually have twice the number of molecules on this side as we do on this side. And that means that this has the greater number of microstates, or the greater positional probability, or another way of saying that is this has the greater entropy, right? This has the lower amount of entropy. Changes in positional entropy is dominated by relative numbers of molecules of gaseous reactants and products. This has the greatest bang for your buck, if you will, in a gaseous media or gaseous phase. If the number of product molecules is greater than the number of reactant molecules, your positional entropy will increase. Your delta S will be positive for that reaction. So let's predict, of course, the reverse is also true, right? If you have greater number of reactant than product, then of course these will reverse and flip around. So predict the sign of delta S naught for each of the following reactions. A, thermal decomposition of solid calcium carbonate. B, oxidation of SO2 in air. Hopefully when you look at these, you can already get a sense for this. This is a solid, this right here has a gas, and we have doubled the number of molecules overall anyways. And so just from the fact that this is a gas, that would already be a huge increase in entropy just from having a gas over here alone. No other considerations really need to be made there. However, we do have twice the number of molecules as well. So the oxidation of SO2 in air. So over here we have 3 molecules. On this side we have 2 molecules of gas. So you would expect its entropy to be greater on this side, wouldn't you? By the way, if you forgot what I said in the previous slide, I of course have the answers on the slides. That's so I can, when I start spacing out when I'm talking about stuff, I can keep on track. Alright, so the third law of thermodynamics. So you have 3 laws of thermodynamics that we're covering here. The entropy of a perfect crystal at 0 Kelvin is 0. So remember, this is a perfect crystal, which is very, very essentially doesn't exist, but at 0 Kelvin, which we've never reached. But this would be the theoretical state. So the perfect crystal at 0 Kelvin, that is the entropy value 0, okay? This is unlike enthalpy and all those other ones. Entropy is an absolute scale, meaning that it has a zero number. It actually does have a zero number, and we don't arbitrarily set that number. It's set by it being a perfect crystal at 0 Kelvin. That is an entropy of 0. Delta H is an arbitrary one. It is not absolute. It is a relative scale. And so the delta H's are 0 for the elements and their preferred phase. That's the delta H is 0. It doesn't have an absolute number, it's 0. Delta S does. Okay, the entropy does. So the entropy of a substance will increase with temperature. The standard entropy values, S naught, will represent increase in entropy that occurs when a substance is heated from 0 Kelvin to 298 Kelvin at 1 atmosphere. The more complex the molecule, the higher the standard entropy values will be. Okay, we've actually, I'm going to mention this here. I think I hit it up a little bit more later on, but I've actually dropped the hint here. This is a great place to show how you can think forward problems and critical think and come up with your own solutions. So I told you the more complex the molecule, the higher the standard entropy value. I've just told you something important about entropy. And that's that if you have a more complex molecule, it gives you greater randomness or greater microstates that you can exist in. And therefore it gives you more possibilities to have greater entropy as well. And so this is actually a true relationship or a something you can extract information further from, right? Okay. Of course, I cannot make every single connection for you. This is just a connection. I wanted to show you how you can make connections. All right. Now, the entropy is a state function of a chemical system. Entropy changes can be calculated just like you did for Hess's law, which was the enthalpy version of this. So you can take these tabulated entropy values from a table for your products times the number of moles of that product. You take the sum of all your products minus the sum of all your reactants, their number of moles times their entropy values from that table. Once you take all of those, you'll get a delta S for your reaction. This works just like Hess's law, where you took those delta H values from tables and then you multiplied them by their coefficient, and then you took the products minus the reactants. That works the exact same way. All right. So keep that in mind. I'm not really going to show you a lot of examples of it because, frankly, you've probably had a lot of Hess's law problems before. And this is actually quite straightforward. Just keep in mind that this right here is your number of moles of those products, right? So if you have something like number of moles of O2, number of moles of CH4, that will be your number of moles of O2, the S naught from the table for O2. Make sure you pay attention to the phase. And then you'd add that to the number of moles of the CH4 times the S naught from the table for the CH4. Add those values together, add up all the reactants, then take your product's number minus your reactants number. This right here, you're typically just going to be doing this for a reaction. So normally you would just use your coefficients and your reactions for these numbers here. These in. All right, so this right here is the entropy of water. And so water molecules have several different vibrations. These right here are the vibrations right here. This is actually showing you rotations. So these vibrations and rotations, they give you freedom of motion. These different states, which are different vibrations you can have and different rotations you can have, give you higher entropies for water. So the more vibrations you have available for water, the higher the entropy it will have. The more rotation states you can have for water, the higher the entropy as well. So I said microstates before, and we really have just focused on positional states as of yet. But it's not just positional states that determine entropy. It's also if you have different molecules going different speeds, these are going to give you a greater entropy. And that's why the temperature is tied to entropy. As you increase temperature, you have more different speeds that the molecules are going to be at, and that will increase your entropy. This also ties into the temperature increasing entropy here. So as you increase the temperature, you have a greater number of possible configurations of molecules having different vibrations, and this can also therefore increase your entropy. By the way, these vibrations here, these are actually what cause, these are done by absorbing typically infrared radiation, and this is actually what makes water a greenhouse gas. A lot of you people didn't know that, did you? Water is the #1 greenhouse gas, actually. It absorbs the most infrared radiation. It causes the greatest impact on the greenhouse effect, which is what causes us to be a higher temperature than Mars. By the way, if you want to see the reverse thing, where you want to see an even greater greenhouse effect, Venus, which is the next closest, which is closer to us than the sun, has a greenhouse effect that's something on the order of like 10,000 times ours, and their temperature at the surface of Venus is 400 something degrees Celsius. So there you go. We have examples of greenhouse effect going both directions right next to us. We have Mars, Earth, and then Venus, showing us different types of greenhouse effect. Right here we see rotations. This actually is what happens with microwaves. So if you've ever wondered how a microwave heats water, the microwave radiation from a microwave oven that bombards the water actually causes it to spin. It causes the water molecules to spin with great amount of energy. And these spinning water molecules sometimes collide and cause them to start bouncing around everywhere, and that increases temperature. And that's actually how a microwave works. Anyways, of course, if you have more different rotational states that you can be in, then you will actually have a greater number of different states you are in, microstates, and you'll have a higher entropy for that water. So let's calculate our delta S naught at 25 degrees Celsius for this reaction right here. And so, yes, we are doing a problem with that previous thing we talked about. Now, frankly, there is an easier way I do this. I usually do that on the board, though. It's actually impossible for me to do on these slides. And so what I would normally do on the board, and the easiest way to do these problems, is you take these values from the tables here, you list them under here. So for example, O2, gas, is this value right here. So we'd put 205 down here. And then NiO, we'd put 38 here. SO2, we'd put 248 here. And then NiS, we would put 53 here. The next thing I would do is I'd surround each of these by parentheses, and I would put their coefficient out in front of them. So 2, 3, 2, 2. Then I would multiply each of these. So 2 times 53, 106. 3 times 205, 600 something. 2 times SO2, you get the idea. Okay, so once I get all those multiplied values, I would then go, okay, so it's always products minus reactants, isn't it? See that? Products minus reactants. So it's final minus initial anytime you do any delta, right? Change in. And so this is final, initial. And so I would then change these numbers that I made from these multiplications to negatives, or these numbers here to negatives, giving you a negative, whatever that was again, 106, negative 600 something. I would then just add all these together. And you notice that it organizes all your data, and it makes this problem actually very fast and trivial, because you can just do everything without having to rewrite a bunch of stuff and doing a lot of work. Anyways, I'll do it with the formula because honestly speaking, it's just impossible for me to actually organize that on a slide. It does not work at all. All right, so I'll try to get it as close to organized as possible. So here we have our product. Here we have our reactants. These are our coefficient values. These are negative because we're on the negative side. This is positive because they're products. All right, we then substitute in, this is this, this is this one right here is this one right here is this one. And so we substitute each of these in from the table. We do the math for each of them, add, subtract, and we will get these. So these are the multiplications first. We then add and subtract, and we get an overall delta S naught of negative 149 joules over Kelvin. Okay, so one of the things you should always do is when you get an answer, it doesn't make sense. So here we have 3 oxygens, gaseous oxygens. Here we have 2 gaseous particles. Here we have 5 versus 4. And so we would expect, because we have less gaseous molecules in the product, that this delta S would be negative. It would lose entropy. All right, again, these are just exercises. You can practice this, and those are what you should get from it. All right, so the change in G that will occur, Gibbs free energy that will occur if the reactants in their standard states are converted to the products in their standard states. More negative the value of delta G, the further reaction shifts to the right to attain equilibrium. So how can we go about dealing with delta G's? Well, delta G's are state functions. So we can do the exact same thing we did with Hess's law, which is we can have tabulated delta G's for different parts of reaction. And we can then just add them and subtract them, just very similar to what we just did, and very similar to Hess's law. You can use the standard free energy of formation, and that's going to be what the tabulated values are for. They will be standard values for formation. Now, if you remember from the HFs, that's the enthalpies of formation, these were for the elements assembling into these substances right here. So we'll go ahead and try this out real quick. Oftentimes my explanation for it is somewhat extraneous. Really just doing it. It's actually not that hard once you've done it. And so that's usually the easier way to deal with it. All right, so let's calculate the delta H, delta S, and delta G using this data right here for this reaction. All right, now we can do Hess's law first, in which case we're going to take these values right here and use them with these. And then we can do the S, we can find the change in enthalpy. And then finally, when we have the change in enthalpy, the change in entropy, we can use those to find our change in Gibbs free energy. And so our delta H, let's go ahead and do that first. We can go ahead and again, products minus reactants. It has the same sort of formula as the previous equation we did. This is called Hess's law in this case. All right, so we have our product right here. We have our reactants here. And again, these are for formations. It's one of the ways you can always remember this. Formations means to make, right? Which is product. So we're going to take our values from those tables for the H's. We will multiply them by our coefficients. And so that will be that times that minus that times that. And then this value right here for oxygen, this is always 0. Because this is actually an element right here. That's the elemental form of oxygen, O2 gas. So, by definition, delta H of formation has to be 0, since that's the definition of formation, assembling it from the elements. So this times this gives us that. This and this gives us that. We add those together, and we get negative 198 kilojoules. Right, the next thing we'll do is the delta S. Again, it's products minus reactants. So we list off our products and reactants. These are absolute values, so none of these are going to be 0 because we're at too high of a temperature. And so again, this is your coefficient, the value from the table for SO3, coefficient, value from the table for SO2, coefficient, value from the table, O2. And you go ahead and do the math, and you get this right here, negative 187 joules per Kelvin. So we've completed 2/3 of this problem now. The only part we have remaining is to determine our delta G. And so we have our delta S, we have our delta H. The only part we need to figure out delta G with is we need a temperature in Kelvin. Now our temperature in Kelvin is actually room temperature, which is 298 Kelvin. Now these are in kilojoules here, and this is in joules here. It's probably easier in this case just to go ahead and work in kilojoules, and so we go ahead and divide this by 1,000 to get into kilojoules. And that'll give you smaller numbers to work with. Alright, so we get negative 198 kilojoules, and this value right here, once we do this math, is 55.7 kilojoules. We add those two together, we get a delta G of negative 142 kilojoules, meaning this reaction is spontaneous. Okay, so use the following data at 25 degrees Celsius, a new problem. Here we have diamond reacting with oxygen, graphite reacting with oxygen to give you CO2. And we can see here they have a very, very similar delta G values. By the way, diamond is very easy to react if you have liquid oxygen. If you spill liquid oxygen on diamond, it will actually poof, turn into CO2 very quickly. Alright, so calculate the delta G then for this following reaction, which is the difference between going from diamond to graphite. So we have two individual reactions. This is diamond on the left here. This one has graphite right here. Notice everything else is the same. So what would happen if we flipped this, which would cause the sign here to flip, right? Because this is a state function. That's like saying going up, downhill, this direction, going uphill, this direction. Well, both directions have the same distance covered, don't they? It's just you're going up in one and down in the other. So the sign changes. Now, we can go ahead and flip this graphite to get the graphite and the products. That would cause oxygens to cancel and the CO2s to cancel, leaving us, if we make the total overall reaction, with carbon diamond going into carbon graphite. By the way, those are called allotropes of each other, if you forgot. Okay, and then we would just take this now positive value and add these together. So let's go ahead and try it out. Here we flipped this one right here, the graphite. We cancel out everything that can be canceled out. See, this is a reactant here, this is a product here. Notice this is flipping the sign right there, negative of a negative. We add those values together then to give us a negative 3 kilojoules. So this actually gives you something kind of interesting that you probably never even thought of before. And that's that the delta G for this is actually negative, right? So a diamond should spontaneously change to graphite at room temperature, room pressure. So your diamond you're wearing is probably spontaneously changing to graphite. However, remember that we are not talking about kinetics, we're just talking about spontaneity, okay? So, that means that, yeah, this may be spontaneously changing graphite. Your diamond you're wearing is spontaneously changing graphite, but it does so slowly that, tens of human lives go by and you don't see any real progress, okay? It's just so slow it doesn't even really matter. Again, this is another great example of kinetics versus thermodynamics. Okay, so kinetic control versus a thermodynamic control. Our diamond is spontaneously going to graphite, sure, but it's happening so slowly we don't even care. So we can say that diamond is kinetically stable with respect to graphite, even though it is thermodynamically unstable. The change in free energy that accompanies the formation of 1 mole of substance from its constituent elements is the definition for the standard free energy of formation, or the delta G naught sub F. All reactants and products are in their standard states. This is used to calculate the free energy change for a reaction, and this would be how you would tabulate delta G values. So you could directly apply a Hess's law, Hess's law like problem, if you will. Same sort of thing we just did with the delta H's and the delta S's, right? Just in this case, delta G. So the delta GF of an element in its standard state would be equal to 0. We've set these as 0 for all these values. So right here, let's go ahead and do a problem again. Really, these are best learned just by practicing. So here we have methanol. It's a high octane fuel commonly used in racing engines. It's reacting and being burned using oxygen to form CO2 and water. So the following energies of formations are then provided, so we can predict the spontaneity of this reaction. Hopefully you would look at this and going, this is burning. I bet this is a negative delta G for being spontaneous. Hopefully you use a little common sense when you do these, so you can guide your problem solving a little bit. Now, again, we're just going to do the same thing we did before, products minus reactants. So these are our products, CO2, water. These are the coefficients in front of them. Those are our reactants, O2, methanol, and their coefficients in front of them. We grab the values from the table. Make sure you double check the phase they're in. So then this is this, of course, this is that one, and this is that one. Notice, by the way, that is oxygen. That is the elemental form of oxygen, so that is 0. All right, we then do the math, and delta G naught is going to be negative 1,378 kilojoules, which hopefully you are not surprised about because that is a combustion. So we would have expected that to be spontaneous. In fact, that spontaneity is what's driving your race car. So if that was not spontaneous, the race car would not be powered by this reaction. This has very large magnitude and a negative sign for the delta G. That indicates it's very favorable thermodynamically, which you probably aren't surprised about because it is driving a race car, right? Yeah, race cars go fast. They very spontaneously move. So non-spontaneous reactions. So for a reaction to be spontaneous, the value of delta G must be less than 0 at constant pressure and temperature. Reactions for which delta G are greater than 0 can be made to proceed by applying external energy. That's like pushing that boulder up the hill versus letting it roll down. Coupling the unfavorable reactions to thermodynamically favorable ones. So the race car does not spontaneously go up the hill, right? But because we have coupled that burning methanol to the race car going up the hill, we have thus overcome that thermodynamically unfavorable, non-spontaneous moving up the hill. This is actually what's used in a lot of this. This is pretty much why ATP exists, by the way. If you're a biology, biochemistry person, ATP, adenosine triphosphate, that's what powers human cells, right? Or that's at least the analogy you've probably been given it at this point. What that actually is doing is it's a reaction that couples with thermodynamically unfavorable ones, and thus makes it thermodynamically favorable then, or spontaneous, right? Electrical energy can be used to produce a chemical change by means of an electrolytic cell, and this is actually what we'll cover in in very very soon. Well, in the next chapter actually. And this is actually electricity driving many battery. This is actually how you charge a battery, by the way. Your phone's battery, that's how you're charging it. Electromagnetic radiation may be used because the absorption of photons can initiate a reaction. This is how solar panels work. This is how the plants synthesize sugars. That's all examples of this one right here. So again, this is the example I just gave you actually, which is carbon dioxide to glucose through the process of photosynthesis. And this is using electromagnetic radiation to couple with what would normally be a non-spontaneous reaction and drive that non-spontaneous reaction forward, despite the fact that it is not spontaneous. It actually is spontaneous going in this direction. By the way, you will notice these photosynthesis reactions are actually the opposite of a combustion reaction. So hopefully you aren't surprised. This is actually spontaneous going towards the left, or the CO2, right? All right, so the free energy and pressure. System under constant pressure and temperature proceeds spontaneously in the direction that lowers its free energy. The free energy of a reaction system changes as the reaction proceeds. This will depend on the pressure of a gas or on the concentration of the species in the solution. This is actually what we're seeing when those equilibrium rates of reactions. Remember how when you consumed your reactant, that got slower and slower and slower, it was less and less spontaneous, and the rates slowed down so they could equal the rates going the opposite direction. That's actually what you're seeing right here. And so the equilibrium, this is the point where the free energy value is at its lowest, which would be 0. And by the lowest, I mean the lowest number, not negative, okay? 0. Okay. So for ideal gases, enthalpy is not pressure dependent. Entropy depends on pressure due to its dependence on the volume. So at a given temperature for 1 mole of ideal gas, S for a large volume will be greater than S for a small volume. Or another way of thinking about this is S for a low pressure, that means they're not squeezed together as much, is going to be greater than S at a high pressure. High pressure would be where your gas molecules are all squeezed tighter together. So free energy and pressure. Rg, we can see the Gibbs free energy is equal to the Gibbs free energy at 1 atmosphere plus RT, universal gas law constant, times the temperature in Kelvin, times the natural log time of the pressure. And so what you can see here is this is actually your pressure dependence of your free energy. Okay, so the concentrations were another thing that we talked about our Gibbs free energy being related to. So again, as your concentrations go down, you become less spontaneous to go forward in your reaction, right? All right, so right here, this is going to be the Gibbs free change in Gibbs free energy equals the change in Gibbs free energy naught, which is the one at 1 atmosphere, plus RT, again, same universal gas law constant, times the temperature. This one right here, by the way, is in joules, Kelvin, mole, because you want this in energy. Be careful about that. There's also, of course, the one you use in the ideal gas law. That would not be your correct units. Okay, the temperatures in Kelvin. This right here is the natural log of the reaction quotient. Now, if you remember, that reaction quotient is just like the equilibrium expression. It's just we don't have to be at equilibrium. And so, this actually gives you two little hints. First, that is products of reactants, right? This is going to have the concentration of your products to the power of their coefficients over the concentration of reactants to the power of their coefficients, just like you did before. The other thing this gives you is, hey, Q here was directly related to K, wasn't it? And so, if you're at equilibrium, which is K, then your delta G here actually has to be 0. All right, so one method for synthesizing methanol involves reacting carbon monoxide and hydrogen gases. An interesting side note to this is there was just an article a month or two ago before doing this lecture. So summer 2020, if you get this later, if I still have this posted up, that the two people came up with a vastly more energy efficient way of doing this same reaction. And this might actually solve the entire global warming crisis because they figured out how to also do a very efficient reaction where they go from carbon dioxide to carbon monoxide. And so this will be a way of consuming the carbon dioxide to make things like methanol, but plastics and all sorts of other substances, which is amazing. It actually, huge deal. If they can actually get a product out within the next 3 or 4 years, that will actually probably solve the global warming crisis. But, cross your fingers. It's just likely not. I mean, you know how things work out. All right, so we have this reaction here. Let's calculate our delta G at 25 degrees Celsius for this reaction, where carbon monoxide gas at 5 atmospheres and hydrogen gas at 3 atmospheres are converted to liquid methanol, which is this reaction. Okay, so to calculate the delta G for this process, we're going to use that equation that we talked about before, which is the delta G equals delta G naught plus RT natural log Q. So the first thing we want to do is get the delta G naught from the standard free energies of formation. So this right here is the standard free energy of formation of the methanol. That right there is the H2 because it's the element. And that right there is the carbon monoxide. So we go ahead and plug these in. These are all multiplied by 1. And this doesn't matter. So we take, again, products minus reactants. We do the math. We go ahead and get this in joules because our R is in joules. All of our other values are in joules. It'll be easier to work with in joules. So one might call this the book value of delta G, or the value of delta G naught for 1 round of the reaction, or for 1 mole of the entire reaction. So the delta G naught value is better written as joules per mole of the reaction, or joules mole reaction. It's just an abbreviation. Use this value to calculate the value of delta G then. So we have delta G naught, R, T, again in Kelvin. We have to get our Q. So again, we get our Q by taking products over reactants, right? And our product here is a pure liquid. So we have 1 on the top in the numerator. Our pressure, partial pressure of our carbon monoxide was 5. It's to the power of 1. Our partial pressure of H2 was 3, and that's the power of 2. Now, you may have noticed we dropped that 2 up here when we did the delta G stuff because that was a 0. Anything multiplied by 0 is 0, right? All right, so we plug those in, we do our math, and we get this value right here for Q, which is 2.2 times 10 to the negative second. So the pure liquid methanol, we again do not include because it's a pure liquid that goes to unity or 1, right? So now we have everything we need to plug in. We have our delta G naught, we have our R, which is a constant, which is what I gave you on that periodic table thing, T, which is our temperature, which we were given, but we need to turn into Kelvin, natural log of Q, which we just figured out. We go ahead and do our math, and we get that this is negative 38 kilojoules per mole of reaction. All right, so the delta G is significantly more negative than the delta G naught. This implies that the reaction is more spontaneous at reactant pressures greater than 1 atmosphere. This result actually is what we'd expect from Le Chatelier's principle. The greater the pressure of the reactants, the more they're going to collide and the more they're going to react, right? And so that's exactly what we expect. It becomes more spontaneous the more reactants we have, right? So the meaning of a delta G for a chemical reaction. Even when the value of delta G provides information regarding whether the system is favored under a given set of conditions, the system may not proceed to pure products if delta G is negative. The system may not remain at pure reactants if delta G is positive. The system will spontaneously seek equilibrium. So yes, this indicates which direction is favored and which direction it will spontaneously go towards the majority of. But it doesn't tell us exactly what those equilibrium positions will. That's why you do an ice problem, right? So right here, the system can achieve the lowest possible free energy by going to equilibrium, not by going to completion. So right here we see an example of A to B. That's what we've sort of probably had in your head when you thought about delta G's, right? It goes from a larger value to a smaller value and it just rolls down the hill spontaneous. But this is more like a reaction. And so your concentrations are large here, and so it is spontaneous going down the hill. And it uses them up, and it uses them up, and then it gets to a point where so much of them are used up, and we have so much product now that this would actually be our lowest point. And that would be our equilibrium point here. Right here, point B would be trying to use up all of those reactants, going to completion, going to all to products. And remember, and typically in an equilibrium, as you increase the concentration of product, it's going to push back. And so the energy actually gets larger once you get to a certain position, which will be your equilibrium position. So after your equilibrium position, reducing your amount of reactants any further and making more product actually is the higher energy, would actually increase the delta G rather than decrease. So the equilibrium point, this is going to occur at your lowest value of free energy available to the reaction system. So consider the following hypothetical equation where 1 mole of gaseous A is initially placed in a reaction vessel at 2 atmospheres. So the free energy of A would be represented by this equation here. The free energy of B would be represented by this equation here then. Notice the difference being pressure of A versus pressure of B, and delta J of A versus delta G of B. The total free energy of the system would be, well, the total free energy, G, would equal the energy of A plus the energy of B. So what's going to happen when A has a lot of concentration? It's going to have a very large negative delta G pushing it towards making B, right? And this is going to cause A to be consumed and B to increase, like so. Now, as A is consumed, that delta G is going to become smaller and smaller in magnitude. The delta G of B is going to become larger and larger in magnitude. At equilibrium, these two delta G's will become equal, giving you a delta G total of 0, or a delta G of A equals delta G of B. And so, of course, the delta G is 0 when the delta G of products equals the delta G of the reactants. Okay, so the quantitative relationship between the free energy and the value for the equilibrium constant is actually given right here. And so again, this explains how this works, is delta G equals 0 at equilibrium, right? We know that due to the definitions of equilibrium and spontaneity that we've been given. That equals delta G naught for that reaction plus, and remember, the naught, it doesn't take into account concentrations, it doesn't take into account the pressure, it doesn't take into account the reaction conditions, right? So that will be plus RT natural log of K. And so if we solve that, what we see is the delta G naught equals the minus RT natural log of K. There you go. All right, so again, this shows you this relationship in a graphical format. Right here we see this equilibrium lies closer to our product. Over here would be an example of the equilibrium lying closer to the reactants. And so you'd expect to produce more products in this one, more reactants in this one. Here we see this relationship in terms of the amount of A that has been reacted. And so when we reach this 0.75 of the A that has been reacted, we see the delta G gets to a minimum. And that would be where your equilibrium would occur. Once we try to use the rest of that, that would be higher Gibbs free energy, and therefore that would be not part of your equilibrium, right? And so that's just the whole thing, as you see. All right, so again, this is that relationship between delta G and K. If you have a K that's greater than 1, then typically your delta G naught is going to be less than 0. That would mean it would be spontaneous going towards the products. If you have a K that is less than 1, then you would see that its delta G is greater than 0. That means your reaction is spontaneous towards reactants, or another way of saying that is your reaction going towards products is not spontaneous, non-spontaneous. Okay, so let's go ahead and try this out a little bit. So the overall reaction for the corrosion rusting of iron by oxygen is as right here. Using the following data, calculate the equilibrium constant for this reaction at 25 degrees Celsius. So here on this side, we actually have two elements. We have iron, and that's the elemental form, and oxygen, the elemental form. And that is actually making here the iron oxide, which is commonly known as rust. All right, so we're going to go ahead then and determine our delta H and our delta S. So again, products minus reactants. We plug our values in for our products and reactants. This 2 again comes from the coefficient in the reaction. And so you notice that you don't have any, you have zeros for the elements for our delta H formation. And so that's just 2 times that value. We go ahead and put this in joules because it's a little easier to work with. Right here we're doing the delta S, again products minus reactants, and these are just the coefficients here. Remember the S naughts, these are absolute values. They don't have any zeros if you're above 0 Kelvin, okay? So you are going to have values for all those. So again, this is this one. This is for oxygen right there. That's for iron down there. You do your math, you get negative 543 joules per Kelvin. You go ahead and convert your temperature in Celsius to Kelvin, so 298 Kelvin. Plug all those values into our delta G relationship here, and we get a final answer for delta G here of negative 1.490 times 10 to the negative 6 joules. A negative delta G would mean this is spontaneous to rusting. And so let's go ahead and check this out versus our value for K. So delta G, let's get an equilibrium constant for this. So delta G naught, we got that value right here. That's the one we just came up with. Equals negative R, which is a constant, gas law constant, universal gas law constant, times T, or temperature, which you actually already converted to Kelvin, times the natural log of K, which we can solve for. Okay, so we plug each of these in. We go ahead and do the multiplication here. We then divide that over. And so that's that right there, and that's this right here. Notice the negatives have disappeared because we had negatives on both sides here. All right, and so the next thing we do is we do that division right there, and that gives us this value right here. Now, the method to get K out of a natural log. What you need to do is when we do this division, we get 601. You take e to the natural log of K, and that will get rid of e in the natural log. They will cancel. You have to do the same thing to both sides. So you're going to take e to the 601, to the 601 power. And that's going to give you your value of K. Now, well, I'm not even going to bother doing it because it's a huge value. It's just a massive, massive number. This is a very, very large equilibrium constant. This is obviously extremely energetically favorable, right? So the rusting of iron is clearly very favorable from a thermodynamic point of view. However, this is one of those things that is kinetically relatively slow. It's not so slow that you don't, see it after a couple of days, but it is slow enough that yes, to completely rust, most things take years. So let's explore our temperature dependence of K. So our quantitative dependence of K on temperature is actually given by this equation right here that we've actually looked at before, which again has that T right there, right? And so we can isolate K on its own, so the natural log of K by itself here. That will then equal, if we go ahead and substitute delta G for this relationship right here, that will then equal delta H over RT. Notice that then can be separated, 1 over T, plus delta S naught over R. If you go ahead and space things out appropriately and, extract that 1 over T so it's all by itself, you're going to get natural log of K, which would be similar to a Y, right, equals negative delta H naught R, which would be like your M. This would be 1 over T, which would be your X. And this would be delta S naught over R, which would be your B, your y-intercept. And this is your slope, right? And so you can now plot these and get your delta H and delta S from that by just finding a variety of equilibriums and their temperatures they happen at. So if the values of K are determined at the various temperatures, you plot the natural log of K versus 1 over T. This will be a linear relationship. You can fit a line to that and get the slope and the intercept of it, the y-intercept. And this will give you, if you multiply those by negative R and R respectively, those will give you delta H and delta S naught. Notice that delta H and delta S naught are both independent of temperature. So these will be constants throughout this linear equation. They won't change due to temperature. It's delta G that changes with temperature. So the maximum possible useful work obtained from a process at constant temperature and pressure is actually equal to the change in the free energy. So this actually tells you the maximum amount of work you can get out of an engine, exactly how efficient you can make something. This gives you the absolute maximum. Now, realistically speaking, this maximum value, it will be larger than you can ever achieve. But it does give you a basis to work from. So if you're very far away from this W max, this maximum amount of work, then you can make the engine more efficient. You have room to work with. But if you hit up near this W max, then that type of engine can never become more efficient. It's limited by the universe itself, which is thermodynamics. Now, achieving this maximum work available from a spontaneous process, this can occur only via a hypothetical pathway. Any real pathway will always waste energy. By the way, this is one of the reasons why you hear a lot of stuff about like fuel cells versus a combustion engine, which is what we use in most cars now. Though some of you maybe use electric engines now. There's more variety. We're rapidly gaining more variety. Anyways, fuel cells get closer to this maximum W, um, this hypothetical pathway, than a combustion engine normally would be able to. So that's why that's such a big deal. But again, these are a hypothetical pathway. You can never actually reach that maximum amount of work. Reversible process, the universe is exactly the same as it was before a cyclic process. Irreversible process, the universe is different after a cyclic process. All real processes are irreversible. They cannot be perfectly reversed to go back to the original state. I know many of us probably wish that was true, but is not. Characteristics of a real cyclic process. Work is changed to heat in a real cyclic process. So some of your work in every real cyclic process is always going to be lost as heat. Entropy of the universe always increases. So your disorder, your entropy of the universe always has to increase in any real cyclic process. So right here we have a reversible process that is a battery that can be charged, and then the alternator right here is going to charge your battery. The electricity that you gain from that can be used to start your motor. And that's why your battery doesn't drain quickly. That's why it typically stays charged until the battery itself is no good. Because your alternator is continuously charging that battery, then it's being discharged to power things like, well, of course, powers like your radio and stuff, right? But it's being discharged to also power things like your start motor. Okay? And so, state 1, work flows to the starter when it's fully charged. It'll enter state 2 then, which is a discharge state, or in this case, partially discharged, usually a fairly small amount. Next, the work will flow to the battery from this alternator here. And that will enter state 1 again, fully charged. At least that is the theoretical idea. In reality, though, this battery, the reaction inside this battery that stores this electricity, is slowly breaking down. And so that fully charged state is always smaller. Also, some of this is going to escape as heat in both directions. So some of this electricity, this work energy, is escaping as heat energy. And so you do not get all the energy that should have come from here going to your battery. You do not get all the energy from your battery going to your start motor. Some of it ends up as heat. Hopefully none of it discharges as electricity to something nearby and kills a short, but sometimes that happens too. All right, so let's revisit these laws of thermodynamics. This is kind of a funny way of thinking about these, but it's very true, and it's a very useful thing for most engineers. So first law, you can't win. You can only break even. You can't actually win and gain extra, can you? You can only ever break even and gain the maximum amount because you can't create energy. Second law, you can't even break even because the universe always takes its cut in the form of entropy, right? So as we use energy, we degrade its usefulness. Every time we use energy, we get less back. All right, very good. Good luck. Hopefully they understood everything. Let me know if you did not. You have a great day.